Okay, so in this video, we will consider what's called elementary row operations, or in simply put, ERO, elementary row operations. Now we have the augmented matrix. So if you have a linear system, the question will always be to find the solution. Instead of find all solutions to the linear system, we know that using instead of the original equations, the augmented matrix, we can save ourselves half of the writing. The question is now, how do we systematically manipulate the rows of our matrix to allow us to simplify the system so we can write the general solution? And the answer is these so-called elementary row operations. Surprisingly, there are only 3 of them. The first 2 are trivial. The last one is a bit more interesting. So let's go over all 3 row operations, and we'll consider the case of a linear system in 2 equations, 2 variables. And the idea clearly applies to any linear system. No matter how many variables you have, no matter how many equations you have, the row operations will clearly still apply. Suppose we had the system 2x plus 5y equals 4 and 3x plus 7y equals negative 6. Well, let's consider the corresponding augmented matrix. So here's our first row operation, and I'll write x for the x coefficients, y for the y coefficients. So how can we manipulate these equations so that the linear system may look different but still be equivalent? Now the first row operation may not seem very useful, but it will actually be extremely useful, and you will appreciate this when you actually start row reducing, solving linear systems using these row operations. So the first type of row operations is we can swap 2 rows of our matrix. And let's see why that makes sense, right? The order in which we write the equation doesn't matter. We are asking to find all values of x and y that satisfy this equation and simultaneously this equation. Well, if we write the equations backwards, so if we swap them, this is still the same problem, right? And this is obvious. And so you see, by swapping the 2 equations, it's the same as if you had swapped the 2 rows of your augmented matrix, because the first row corresponds to the first equation, the second row corresponds to the second equation. And how do we write this? Well, we'll use the letter R for row and a subscript for the index of the row. So R1 means the first row of our matrix, R2 means the second row. And if we had more than 2 rows, R3 would be the third row, and so forth. We use a double-headed arrow to mean swapping, interchanging. So it's simply right here, row 1, double-headed arrow, row 2. So this means swap row 1 and row 2. And now you get a different looking augmented matrix. Again, we no longer write x and y, we only write this first. So we swap these 2 rows, so row 2 becomes row 1, 3, 7, negative 6. And row 1 becomes row 2, 2, 5, 4. Clearly, solving this system is the same as solving this one, therefore, having this augmented matrix is equivalent to having this augmented matrix. And that is our first type of row operation. We can swap any 2 rows. So we can take row I, where I could be 1, 2, 3, 4, any positive integer, and we can swap row I with row j. J could be also any other positive integer. Clearly though different from j, because if you swap row I with row I, nothing has taken place. And that is our first row operation. Again, it's a trivial row operation on the surface, but it will be quite useful in implementing these operations systematically. Let's look now at our second type of row operations. Let us rewrite the linear system. 2x plus 5y equals 4. 3x plus 7y equals negative 6. And we have, as before the augmented matrix, well, clearly, if we multiply a row throughout by a non-zero constant, then the equation is equivalent, right? Suppose that I would multiply this row by, let's go with 8. Since 2x plus 5y is equal to 4, then I can do 8 times the left-hand side. 2x plus 5y equals 8 times the right-hand side, right? This is perfectly justifiable. If 2x plus 5y equals 4, so if this equals 4, then clearly I can multiply both sides by 8. And of course, 8 is an arbitrary choice here. I could replace 8 by any non-zero constant k, right? So we'll do it simultaneously just to see that 8 is an arbitrary choice. So you could also multiply the left-hand side by k. So k times the left-hand side, 2x plus 5y, equals k times the right-hand side, which is 4. Let's multiply this out and see what happens. We'll get 8 times 2x, which is 16x, plus 8 times 5y, which is 40. Y equals 8 times 4, 32. If you multiply across by k, you'll get k times 2x plus k times 5y plus, or equals, k times 4. And let's see what happens now when we leave the second row unchanged, so we don't touch this one for now. So 3x plus 7y equals negative 6. And we'll leave this one unchanged. If k is any non-zero entry, non-zero real number, then the equation 2x plus 5y equals 4, and the equation k times 2x plus k times 5y equals k times 4 is equivalent to the original equation. As you can obviously go backwards. If you multiply by 1 over k, you will obtain the original equation. 2x plus 5y equals 4. And so you can go back and forth, and that's why this operation of multiplying an equation by a non-zero number is giving an equivalent linear system. And so, if you write the end result, the first equation is this, k times 2x plus k times 5y plus k times 4, and this is our second equation. But now think of what would happen to the augmented matrix of this linear system, which is equivalent to the original one. Let's see. The second equation is the same as the original system, and so we can simply rewrite it. 3, 7, negative 6. Look now at the first row. It would be k times 2x k times 5y equals k times 4. So look what's happened from here to here. Quite simply, we have multiplied row 1 by k. And you multiply a row by k, of course, by multiplying every entry by k. So k times 2, k times 5, k times 4. And this is our second row operation. So how do we write this? Well, we are changing row 1. And what are we doing to row 1? We are multiplying row 1 by k. And this is our second type of row operations. We can multiply any row of an augmented matrix by any non-zero real number, as this is equivalent to multiplying an equation of the linear system by this non-zero constant. And it has to be non-zero, because the equation has to be reversible. Think of what would happen if you multiply both sides by 0. Then you get 0 times this, which is 0, plus 0 times this, which is 0, and so you'd get 0 is equal to 0 times 4, which is 0. Now you can't go backwards. You can't go from the equality 0 equals 0 to 2x plus 5y being equal to 4. And that's why k must be non-zero. It must be a reversible operation so that the new linear system is equivalent to the original one. So we can write quite simply k times any row of your choice, where k is any non-zero real number. And this is our second type of row operations. We could have also, if we wanted, multiplied row 2 by a third, by 4 over 7, by negative 6, anything you want as long as it's non-zero. And again, obviously, you multiply a row of the matrix by a real number by multiplying every single entry of the row by this real number. This is now our second row operation. This was our first, this is our second. And now, what is the final and third row operation? This one is not so obvious, but not that complicated either. Let's rewrite the original linear system. So 2x plus 5y equals 4. 3x plus 7y equals negative 6. Again, we have the corresponding augmented matrix. So let's see. Let's first say we do this. Let's multiply the first row by a non-zero real number. So we'll break this down into two steps. Suppose we multiply row 1 by k, where k is not equal to 0. Then the system will be equivalent to this linear system, which will be k times 2x plus k times 5y equals k times 4. And we don't change the second equation. So 3x plus 7y equals negative 6. Now, let's do one more manipulation. We will replace this row now by the original row, because they are, or I should say equation, because they are indeed equivalent. So I'll leave this one unchanged. But I'll do something now to the second equation. Think of it. This is equal to this. So let me add to the left-hand side of the second equation this quantity right here. So this will give us 3x plus 7y plus all of this. So k times 2x plus k times 5y equals, well, negative 6. And now think of it. I've added to the left-hand side of this equality, this quantity. Well, to preserve the equality, I must add it on both sides. But instead of adding this explicitly, I'll add this on the right because they are equal. So I'll simply add on the right instead of this 4k, or k4. And this is still equivalent to this, right? If k2x plus k5y equals k4, then clearly 3x plus 7y plus this equals negative 6 plus this, as both are the same amount. And so this linear system is equivalent to this one, which is also equivalent to this one. But let's rewrite this properly. There's one last thing we can do and simplify. We can rewrite the first equation as we're not changing it. And let's see, there are two multiples of x and there are two multiples of y here. Let's combine them. We'll have 3 times x plus k2 times x. Then plus multiples of y, 7 times y plus k5 times y. And this equals negative 6 plus k4. And so this is what we wanted. So if you look, the original linear system is equivalent to this linear system. And let's see if we can simplify the construction of this one from this one quite easily. Well, if you see, it looks like what we've done is we did 3 plus k2, so 3 plus k times 2. Then we have 7 plus k times 5, so 7 plus k times 5. And then minus 6 plus k times 4, minus 6 plus k times 4. So it seems that all we did was to add to row 2 k times row 1. And let's see if that works. Row 1 has stayed the same. And now we said that we changed row 2, and we did row 2 plus k times of row 1. So we are adding to row 2 a multiple of row 1. So let's see, will this be consistent to our linear system? Well, when we add to a row a multiple of a different row, naturally we will add corresponding entries. So we do row 2, 3 plus k times row 1. So 3 plus k times 2, 3 plus k. 3 plus k times 2, so 3 plus k times 2. And we keep going. Row 2 plus k row 1, so 7 plus k times 5. And finally, row 2 plus k row 1, so negative 6 plus k times 4. Or 4k, same thing. And so you see, indeed, this row corresponds to this linear equation. And so it works out. Because both linear systems are equivalent, both augmented matrices are also equivalent. Now there's one thing that we can do here, is we can actually remove this restriction. Because think of, what if k were 0? If k is 0, then we're saying row 2 plus 0, row 1, which adds nothing, and all we get back is row 2, which changes nothing. We simply get back 3, 7, and negative 6, and so nothing happens. It's actually not a change if k is 0. So we can remove this restriction, because if k is 0, nothing happens. And this is our third and final type of row operations. We can take a given row and add to it some multiple of another row. I and j must be different, of course. And this is our third type of row operations. Let's summarize, and let's show a simple example where we perform one of each numerically with actual choices of numbers. So here's a summary. Our 3 elementary row operations. And what's surprising is, to solve any linear system, no matter how many variables there are, no matter how many equations there are, all we need is to apply these 3 row operations. The first one was the swapping of 2 rows. So we could interchange any 2 rows of the augmented matrix, as long of course as I is different than j, because if I is j, nothing happens. The second row operation was multiplying any given row, but by a non-zero constant. And the third type of row operation, as we have seen, is to add to any given row some multiple of another row, where I is different than j. And of course we could say that k can't be 0, because if it is, then we just replace row I by itself, which is redundant. So we could say k is non-zero, just to make this a non-trivial row operation. And that's it. So in our next video, we will go over quickly how to use these row operations systematically to solve, in the most effective way, any linear system. Let's look at just one short example of performing one row operation to a given augmented matrix, just to get a feel for it. So suppose we take the original augmented matrix, so we'll write the linear system, so it's 2x plus 5y equals 4, 3x plus 7y equals negative 6. The first thing is we construct the augmented matrix of the linear system. Okay, well, just for the fun of it, let's apply the first type of row operation, which is swapping of 2 rows. As there are only 2 rows here, we don't have any option. We have to swap row 1 with row 2. So we interchange the 2 rows. So we'll get 3, 7, negative 6, 2, 5, positive 4. Both matrices will give us equivalent linear systems. Then we can multiply a row of our choice by a non-zero constant. Well, let's multiply, say, row 1 by 1/3. So let's do 1 over 3 times row 1. As 1 over 3 is non-zero, this is justifiable. Since we are only changing row 1, we can first recopy row 2, so as not to make any mistake. And when we multiply a row by a scalar, by a real number, we multiply every entry by that very same scalar. So 1 over 3 times 3 is 1. 1 over 3 times 7, 7 over 3. 1 over 3 times negative 6, negative 2. Okay, let's now apply our third type of row operation, adding, of course, if we take k to be negative, that's the same as subtracting to a row a multiple of another row, right? Because we're saying to row I we add k times row j. Well, if k is negative 3, for example, then it would be row I plus minus 3 times row j. So we can add or subtract the multiple of a row to a different row. Well, let's kill this entry using our 1 here. Let's do row 2 minus, and we'll do minus 2 times row 1. Let's see what comes out of this. We are subtracting twice of row 1 to row 2. This is an allowed row operation. Before we do so, let's recopy row 1 as we are not changing it. So let's apply this row operation. So row 2 minus 2 of row 1. So 2 minus 2 times 1 is minus 2. 2 minus 2 is 0. 5 minus 2 times 7/3. Let's do this on the side. So 5 minus 2 times 7/3. This is 5 minus 14/3. Over 3, 5 is 15, so it's 15/3 minus 14/3, and all we get is 1/3. And 4 minus 2 times negative 2, well, negative 2 times negative 2 is plus 4. 4 plus 4 is 8. And now we've applied a third type of row operation. So first type, swapping of two rows. Second type, multiplying a row by a non-zero real number. Third type, adding or subtracting a multiple of a row to a different row. And that's it. So those are the three types of row operations. Now the only question left over is, how do we systematically use these row operations to solve any linear system? And this will be the topic of our next video. We'll go over the algorithm, the sequence of steps, very roughly, and then in the following videos you'll see several examples of how to implement this idea explicitly.